Hello friends, in this session we will discuss algebraic operations of sequences as a special case of algebraic operations of functions. We will see that limit rules of functions, the sum rule, difference rule, product rule, constant multiple rule and quotient rule are applicable also for sequences. We will describe the sandwich theorem for sequences. A number of examples will be described to get a good understanding of the concepts. Algebraic operations of sequences. We have seen that algebraic operations of functions are defined pointwise. Since sequences are functions with domain as the set of positive integers, it is natural to define algebraic operations of sequences termwise. More precisely, if x equal to sequence un and y equal to sequence vn are sequences of real numbers, the sum of x equal to sequence un and y equal to sequence vn is defined to be the sequence x plus y equal to sequence un plus vn. That is, x plus y of n equal to x of n plus y of n, which is equal to un plus vn. Similarly, we define their difference to be the sequence x minus y equal to sequence un minus vn and their product to be the sequence x into y equal to sequence un vn. If C belongs to R, we define the multiple of x by C to be the sequence Cx equal to sequence Cun. Finally, if Z equal to sequence Wn is a sequence of real numbers with the Wn not equal to 0 for all n belongs to n, then we define the quotient of x and z to be the sequence x upon z equal to sequence of un upon wn. For example, if x and y are the sequences x equal to sequence 2, 4, 6 etc. 2n etc. and y equal to sequence 1 upon 1, 1 upon 2, 1 upon 3 etc. 1 upon n etc. then we have x plus y equal to sequence 3 upon 1, 9 upon 2, 19 upon 3 etc. 2n square plus 1 upon n etc. x minus y equal to sequence 1 upon 1, 7 upon 2, 17 upon 3 etc. 2n square minus 1 upon n etc. x into y equal to sequence 2, 2, 2 etc. 2 etc. 3x equal to sequence 6, 12, 18 etc. 6n etc. x upon y equal to sequence 2, 8, 18 etc. 2n square etc. We note that if Z denotes the sequence Z equal to sequence 0, 2, 0 etc. 1 plus negative 1 whole power n etc. then we can define x plus z, x minus z and x into z. But x upon z is not defined since some of the terms of z are equal to 0. Now we state limit rules for sequences. Theorem, limit rules for sequences. Let sequence un and sequence vn be sequences of real numbers. The following rules hold if limit un as n approaches infinity equal to a and limit of vn as n approaches infinity is b, where a and b are real numbers. First one, sum rule. Limit of un plus vn as n approaches infinity equal to a plus b. Second one, difference rule. Limit of un minus vn as n approaches infinity is a minus b. Third one, product rule. Limit of un into vn as n approaches infinity is a into b. Fourth one, constant multiple rule. Limit of k times vn as n approaches infinity is k times b for any number k. Fifth one, quotient rule. Limit of un upon vn as n approaches infinity is a upon b if b not equal to 0. We only prove the sum rule, leaving the rest to the exercise. To show that limit of un plus vn equal to a plus b, we need to estimate the magnitude of absolute value of un plus vn minus a plus b. To do this, we proceed as follows. Absolute value of un plus vn minus a plus b equal to absolute value of un minus a plus vn minus b, which is less than or equal to absolute value of un minus a plus absolute value of vn minus b, using the fact that the absolute value function satisfies the triangle inequality absolute value of a plus b less than or equal to absolute value of a plus absolute value of b. By hypothesis, if epsilon greater than 0, there exists a natural number k1 such that if n greater than or equal to k1, then absolute value of un minus a less than epsilon by 2. Also, there exists a natural number k2 such that if n greater than or equal to k2, then absolute value of vn minus b less than epsilon by 2. Hence, if k equal to supremum of k1 k2, it follows that if n greater than or equal to k, then absolute value of un plus vn minus a plus b less than or equal to absolute value of un minus a plus absolute value of vn minus b, which is less than 1 by 2 times epsilon plus 1 by 2 times epsilon, which is equal to epsilon. Since epsilon greater than 0 is arbitrary, we have the sequence un plus vn converges to a plus b. This completes the proof. Using the theorem on limit rules and the limit results in the preceding session, evaluate the limits of the following sequences. First one, sequence negative 1 upon n. Second one, sequence n minus 1 upon n. Third one, sequence 5 upon n square, and fourth one, sequence 4 minus 7 n raised to 6 upon n raised to 6 plus 3. We find the limit as follows. First one, limit of negative 1 upon n as n approaches infinity equal to negative 1 times limit of 1 upon n as n approaches infinity by the constant multiple rule, which is equal to negative 1 times 0, since limit of 1 upon n as n approaches infinity is 0, which is equal to 0. Second one, limit of n minus 1 upon n as n approaches infinity equal to limit of 1 minus 1 upon n as n approaches infinity, which is equal to limit of 1 as n approaches infinity minus limit of 1 upon n as n approaches infinity by the difference rule, which is equal to 1 minus 0, which is equal to 1. Third one, limit of 5 upon n square as n approaches infinity equal to 5 times limit of 1 upon n as n approaches infinity into limit of 1 upon n as n approaches infinity using the constant multiple rule and the product rule, which is equal to 5 into 0 into 0, which is equal to 0. And fourth one, limit of 4 minus 7 n raised to 6 upon n raised to 6 plus 3 as n approaches infinity equal to limit of 4 upon n raised to 6 minus 7 upon 1 plus 3 upon n raised to 6 as n approaches infinity, which is equal to limit of 4 upon n raised to 6 minus 7 upon 1 plus limit of 3 upon n raised to 6 as n approaches infinity using the quotient rule, which is equal to 0 minus 7 upon 1 plus 0, which is equal to negative 7. We show that limit of 2n plus 1 upon n as n approaches infinity is 2. Since 2n plus 1 upon n equal to 2 plus 1 upon n, we have limit of 2n plus 1 upon n as n approaches infinity equal to limit of 2 plus 1 upon n as n approaches infinity, which is equal to limit of 2 as n approaches infinity plus limit of 1 upon n as n approaches infinity, which is equal to 2 plus 0, which is equal to 2. We show that limit of 2n plus 1 upon n plus 5 as n approaches infinity is 2. We have limit of 2n plus 1 upon n plus 5 as n approaches infinity equal to limit of 2 plus 1 upon n upon 1 plus 5 upon n as n approaches infinity, which is equal to limit of 2 plus 1 upon n as n approaches infinity upon limit of 1 plus 5 upon n as n approaches infinity using quotient rule, which is equal to 2 plus 0 upon 1 plus 0, which is equal to 2. We show that limit of 2n upon n square plus 1 as n approaches 0 is 0. We have limit of 2n upon n square plus 1 as n approaches infinity equal to limit of 2 upon n upon 1 plus 1 upon n square as n approaches infinity, which is equal to limit of 2 upon n as n approaches infinity upon limit of 1 plus 1 upon n square as n approaches infinity, which is equal to 0 upon 1, which is equal to 0. Remark to limit rules for sequences. One consequence of theorem on limit rules for sequences is that every non-zero multiple of a divergent sequence un diverges. For suppose to the contrary that sequence C un converges to some number c not equal to 0. Then by taking k equal to 1 upon c in the constant multiple rule, we see that the sequence 1 upon c into c un equal to sequence un converges. Thus, sequence c un cannot converges unless sequence un also converges. Hence, if sequence un does not converges, then sequence c un does not converges. Sometimes the even numbered and odd numbered terms of a sequence behave sufficiently differently that it is desirable to investigate their convergence separately. The following theorem, whose proof is omitted, is useful for the purpose. Theorem: a sequence converges to a limit L if and only if the sequence of even numbered terms and the odd numbered terms both converges to L. That is, for the sequence un, limit of un as n approaches infinity is L if and only if limit of u 2n as n approaches infinity is L and the limit of u 2n plus 1 as n approaches infinity is L. As an example, the sequence 1 upon 3, 1 upon 4, 1 upon 3 square, 1 upon 4 square, 1 upon 3 cube, 1 upon 4 cube, etc. converges to 0 since the even numbered terms 1 upon 4, 1 upon 4 square, 1 upon 4 cube, etc. and the odd numbered terms 1 upon 3, 1 upon 3 square, 1 upon 3 cube, etc. both converges to 0. But the sequence 5, 1 upon 2, 5, 1 upon 2 square, 5, 1 upon 2 cube, etc. diverges since the even numbered terms 1 upon 2, 1 upon 2 square, 1 upon 2 cube, etc. converges to 0 and the odd numbered terms 5, 5, 5, etc. converges to 5. In this session, the limit laws we have familiarized with the sandwich theorem for functions. Suppose that g of x less than or equal to f of x less than or equal to h of x for all x in some open interval containing c, except possibly at x equal to c itself. That is, f of x is sandwiched between the function g of x and h of x in some open interval containing c, except possibly at c. Suppose also that limit of g of x as x approaches c equal to limit of h of x as x approaches c equal to L. Then limit of f of x as x approaches c is also L. Since sequence of functions with domain the set of natural numbers, the above theorem is applicable for sequences also, provided one sequence is sandwiched between two other convergent sequences converging to the same limit. The formal statement follows. The sandwich theorem, squeezing theorem for sequences. Let sequence un, sequence vn and sequence wn be sequences of real numbers. If un less than or equal to vn less than or equal to wn holds for all n beyond some index n, and if limit of un as n approaches infinity equal to limit of wn as n approaches infinity equal to L, then limit of vn as n approaches infinity is L. As an example, we show that sequence 1 upon 2 power n converges to 0. We have 0 less than or equal to 1 upon 2 power n less than or equal to 1 upon n, and since limit of 1 upon n as n approaches 0 is 0, with the un equal to 0, vn equal to 1 upon 2 power n and wn equal to 1 upon n, the sandwich theorem implies that limit of 1 upon 2 power n as n approaches infinity is 0. In the following example, we use the Bernoulli's inequality. If x greater than negative 1, then 1 plus x whole power n greater than or equal to 1 plus nx for all positive integer n. If 0 less than b less than 1, then we show that limit of b power n as n approaches infinity is 0. Since 0 less than b less than 1, we can write b equal to 1 upon 1 plus a, where a equal to 1 upon b minus 1, so that a greater than 0. By Bernoulli's inequality, we have 1 plus a whole power n greater than or equal to 1 plus na. Hence, 0 less than b power n equal to 1 upon 1 plus a whole power n less than or equal to 1 upon 1 plus na, which is strictly less than 1 upon na. And since limit of 1 upon na as n approaches infinity equal to 1 upon a into limit of 1 upon n as n approaches infinity equal to 0, we get limit of b power n as n approaches infinity is 0 by sandwich theorem. As another example, we show that if limit of absolute value of a n as n approaches infinity equal to 0, then limit of a n as n approaches infinity is 0. The main thing to do this proof is to note that negative of absolute value of a n less than or equal to a n less than or equal to absolute value of a n. By assumption, limit of absolute value of a n as n approaches infinity is 0, and then by application of constant multiple rule, limit of negative absolute value of a n as n approaches infinity equal to negative times limit of absolute value of a n as n approaches infinity, which is equal to 0. Then we have by sandwich theorem that limit of a n as n approaches infinity is 0. We bring your attention to note that if a not equal to 0, limit of absolute value of a n as n approaches infinity equal to a need not imply limit of a n as n approaches infinity equal to a. For example, if sequence a n equal to sequence negative 1, negative 1, negative 1 etc., then the sequence absolute value of a n equal to sequence 1, 1, 1 etc., so that limit of absolute value of a n as n approaches infinity is 1, but limit of a n as n approaches infinity is negative 1. We observe from the sandwich theorem is that if absolute value of v n less than or equal to w n, then limit of w n as n approaches infinity is 0, then limit of v n as n approaches infinity is 0, because negative w n less than or equal to v n less than or equal to w n. As an illustration, the sequence negative 1 power n into 1 upon n converges to 0, since the sequence negative 1 power n into 1 upon n less than or equal to 1 upon n, and limit of 1 upon n as n approaches infinity is 0. Also, sequence sin n upon n converges to 0, since absolute value of sin n upon n, which is equal to absolute value of sin n upon n, which is less than or equal to 1 upon n, and limit of 1 upon n as n approaches infinity is 0. Now, if a greater than 0, we show that limit of 1 upon 1 plus n a as n approaches infinity is 0. Since a greater than 0, it follows that 0 less than n a less than 1 plus n a. Therefore, we conclude that 0 less than 1 upon 1 plus n a less than 1 upon n a, which is evidently implies that absolute value of 1 upon 1 plus n a less than or equal to 1 upon a into 1 upon n for all n belongs to natural number n. Since limit of 1 upon n as n approaches infinity is 0, we may invoke constant multiple rule with k equal to 1 upon a and get that limit to the right of the inequality as limit of 1 upon a into 1 upon n as n approaches infinity is 0. Hence, limit of 1 upon 1 plus n a as n approaches infinity is 0. Theorem, the continuous function theorem for sequences. Let sequence un be a sequence of real numbers. If un converges to L and if f is a function that is continuous at L and defined at all un, then f of un converges to f of L. As an illustration, we show that square root of n plus 1 upon n converges to 1. We know that n plus 1 upon n equal to 1 plus 1 upon n converges to 1 as n approaches infinity. Taking f of x equal to square root of x, the square root function and L equal to 1, and noting that square root function is continuous at 1, the theorem implies that square root of n plus 1 upon n converges to square root of 1, which is equal to 1. Using L'Hopital rule theorem, suppose that f of x is a function defined for all x greater than or equal to n naught, and that sequence un is a sequence of real numbers such that un equal to f of n for n greater than or equal to n naught. Then limit of f of x as x approaches infinity is L implies limit of un as n approaches infinity is L. To prove this, suppose that limit of f of x as n approaches infinity is L. Then for each positive number epsilon, there is a number m such that x greater than m implies absolute value of f of x minus L less than epsilon. Let n be an integer greater than m and greater than or equal to n naught. Then n greater than n implies un equal to f of un and absolute value of un minus L equal to absolute value of f of n minus L, which is less than epsilon. Hence, limit of un as n approaches infinity is L. This completes the proof. That is, we have shown that corresponding to epsilon greater than 0, there is a positive integer n such that n greater than n implies absolute value of un minus L less than epsilon. As an illustration of this fact, we show that limit of natural log n upon n as n approaches infinity is 0. The function natural log x upon x is defined for all x greater than or equal to 1 and agrees with the given sequence natural log n upon n at positive integers. Therefore, by the theorem, limit of natural log n upon n as n approaches infinity will be equal to limit of natural log x upon x as x approach infinity. If the latter exists, now limit of natural log x upon x as x approaches infinity is in the form infinity upon infinity form. Therefore, limit of natural log x upon x as x approaches infinity equal to limit of 1 upon x upon 1 as x approaches infinity using L'Hopital rule, which is equal to 0 upon 1, which is equal to 0. We conclude that limit of natural log n upon n as n approaches infinity is 0. Working method. When we use L'Hopital rule to find the limit of a sequence, we often treat n as a continuous real variable and differentiate directly with respect to n. This saves us from having to rewrite the formula for un as we did in the previous example. We find limit of 2 power n upon 5n as n approaches infinity as follows. Limit of 2 power n upon 5n as n approaches infinity is in the infinity upon infinity form. Hence, limit of 2 power n upon 5n as n approaches infinity is limit of 2 power n into natural log 2 upon 5 as n upon infinity, applying L'Hopital rule and noting that the derivative of 2 power n with respect to n is 2 power n natural log 2, which is equal to infinity. Table limits of sequences. First one, limit of natural log n upon n as n approaches infinity is 0. Second one, limit of nth root of n as n approaches infinity is 1. Third one, limit of x power 1 upon n as n approaches infinity is 1 for x greater than 0. Fourth one, limit of x power n as n approaches infinity is 0 for absolute value of x less than 1. Fifth one, limit of 1 plus x upon n whole power n as n approaches infinity is e power x for any x. Sixth one, limit of x power n upon n factorial as n approaches infinity is 0 for any x. In the limits 3 to 6, x remains fixed as n approaches infinity. We use the above table to evaluate the following limits. First one, limit of natural log n square upon n as n approaches infinity equal to limit of 2 times natural log n upon n as n approaches infinity using L'Hopital rule, which is equal to 2 times 0, which is equal to 0. Second one, limit of nth root of n power 2 upon n as n approaches infinity equal to limit of n power 1 upon n whole square as n approaches infinity, which is equal to limit of n power 1 upon n as n approaches infinity whole square, which is equal to 1. Third one, limit of nth root of 3n as n approaches infinity equal to limit of 3 power 1 upon n into n power 1 upon n as n approaches infinity, which is equal to limit of 3 power 1 upon n as n approaches infinity into limit of n power 1 upon n as n approaches infinity, which is equal to 1. Fourth one, limit of negative 1 upon 2 whole power n as n approaches infinity equal to 0 using formula 4 with x equal to negative 1 upon 2. Fifth one, limit of n minus 2 upon n whole power n as n approaches infinity equal to limit of 1 plus negative 2 upon n whole power n as n approaches infinity, which is equal to e power negative 2 using formula 5 with x equal to negative 2. Sixth one, limit of 100 power n upon n factorial as n approaches infinity is 0 using formula 6 with x equal to 100. Seventh one, with x equal to 0.03 greater than 0 using formula 3, limit of 0.03 whole power 1 upon n as n approaches infinity is 1. Eighth one, with x equal to 7 using formula 5, limit of 1 plus 7 upon n whole power n as n approach infinity is e power 7. Ninth one, using formula 3 and 2, limit of nth root of 10n as n approaches infinity equal to limit of 10 power 1 upon n into n power 1 upon n as n approaches infinity, which is equal to 1 into 1, which is equal to 1. Tenth one, using formula 2, limit of nth root of n square as n approaches infinity equal to limit of nth root of n whole square as n approaches infinity, which is equal to 1 square, which is equal to 1. 11th one, using formula 2 with x equal to n plus 4, limit of n plus 4 whole power 1 upon n plus 4 as n approaches infinity equal to limit of x power 1 upon x as x approaches infinity, which is equal to 1. 12th one, using formula 6, limit of n factorial upon 10 power n as n approaches infinity equal to 1 upon limit of 10 power n upon n factorial as n approaches infinity, which is equal to infinity, hence diverges. 13th one, using formula 6, limit of n factorial upon 2 power n into 3 power n as n approaches infinity is limit of 1 upon 6 power n upon n factorial as n approaches infinity, which is equal to infinity, hence diverges. 14th one, using formula 5, limit of natural log of 1 plus 1 upon n whole power n as n approaches infinity equal to natural log of limit of 1 plus 1 upon n whole power n as n approaches infinity, which is equal to natural log of e, which is equal to 1. Let En equal to 1 plus 1 upon n whole power n for n in n with x equal to 1. Then the formula limit of 1 plus x upon n whole power n as n approaches infinity is e raised to x. Shows that the sequence En is convergent and its limit is e. The limit of the sequence is the famous Euler number e, whose approximate value is 2.71828182459045 etc. We note that e is an irrational number. The letter e was chosen to honor the Swiss mathematician Leonhard Euler, who calculate its value up to 23 decimal places. The number e is the base of the natural logarithm. Hence, it is also known as Napier's constant in honor of Scottish mathematician John Napier, who invented logarithm. The constant was discovered by the Swiss mathematician Jacob Bernoulli while studying compound interest. We now answer the question, does the sequence whose nth term is un equal to n plus 1 upon n minus 1 whole power n converges? If so, find limit of un as n approaches infinity. The limit leads to an indeterminate form 1 power infinity. We can apply L'Hopital rule if we first change it to the form infinity into 0 by taking the natural logarithm of un. Natural log un equal to natural log n plus 1 upon n minus 1 whole power n, which is equal to n times natural log n plus 1 upon n minus 1. Therefore, limit of natural log un as n approaches infinity equal to limit of n times natural log n plus 1 upon n minus 1 as n approaches infinity, which is in infinity into 0 form, which is equal to limit of natural log n plus 1 upon n minus 1 upon 1 upon n as n approaches infinity, which is in 0 upon 0 form, which is equal to limit of negative 2 upon n square minus 1 upon negative 1 upon n square as n approaches infinity applying L'Hopital's rule, which is equal to limit of 2 n square upon n square minus 1 as n approaches infinity, which is equal to limit of 2 upon 1 minus 1 upon n square as n approach infinity, which is equal to 2. Since natural log un approaches to 2 as n approaches infinity and f of x equal to e power x is continuous everywhere, then the theorem tells us that un equal to e power natural log un converges to e square. That is, the sequence un converges to e square. Let us summarize the session. In this session, we describe algebraic operations of sequence and limit rules for sequences. The sandwich theorem for sequences also have been discussed. The concepts were illustrated through various types of examples. Hope you enjoy the session. See you next time. Until then, bye.